Today I'll be covering the second part of this course, which is on wind energy and wind turbine. So the most important properties of the wind is air velocity and air density. Okay, and air density varies with atmospheric conditions and altitude. So the standard atmospheric condition is 1.201. So this is the magic number that we all should know. Okay. And a wind turbine is mostly between only a few hundred meters above ground, and it is adequate for us to use standard atmospheric conditions for air density. Okay, why do I say that? Later on, we will see why. Yeah, and before we derive the theoretical energy and power that we can derive from a particular amount of wind, it is also important for us to know that power is equals to energy over time, and I believe we all know this one. So let's assume that we have a particular volume of air that we are considering right now, and the air is moving through a cross-sectional area of A and moving along a distance x. So A multiplied x will give us the volume of the air that we are considering. And if we take this volume and multiply with the air density at standard atmospheric condition, let's say, and the density of the air is represented by rho, rho of the volume, rho multiplied volume will give us the mass of the air. Okay. So by having the mass of the air, and then we know that kinetic energy is half mv squared, we can substitute the mass of the air that we are considering right now into here, and then we will end up with this form, half rho a x v squared. And remember, just now we said that power is supposed to work over time. This is where we apply the concept over here, because we want to know what is the theoretical power that we can derive from a particular amount of wind. So to do that, I have to take the amount of energy divided by a certain amount of time. So to get the maximum theoretical to get the maximum theoretical power that we can derive from the wind, I simply take the derivations of it and equate it to 0. So I put dke dt. Okay, I take dke dt, and I will end up with this form. Okay, dke dt, and I will this form. So when I put it in this form, I realize that dx dt is also equals to v. Why? Because velocity is the change of distance over time. So I substitute further dx dt equals to v, and I end up with this final form. Okay, half rho av cubed. All right. So several comments that we can derive from here is that the basis of all wind power and energy, this is the basis of all wind power and energy calculations. Okay. So just to let you know in advance, this is the theoretical power that is available in the wind. This is not the power that we can extract from wind turbine. Those are two different things. Okay, we will see later what is the power that we can derive from wind turbine. And the first comment I can make is that the most obvious feature is that the wind power is proportional to the cube of average wind speed. Okay, this is quite obvious. And the second one is that the average wind speed is by far the dominant considerations in wind turbine location, because we know that to extract wind power, it is mainly determined by the cube of v. So this is the most dominant factor, and therefore the wind velocity is the most important factor that we need to consider when calculating wind power that we can extract from a particular amount of wind. All right. So I see you in the next video.